Hello and welcome to part 2 of building a basic global climate model with free simile software. Now, using the tools and skills we acquired in our first episode, we now launch into building a model of an Earth-like planet. We ended last time noting that the Earth with no atmosphere should look like a leaky bucket, but instead of water pouring in one way and out another way, we have energy pouring in from the sun, and energy re-radiating out from the planet back to space. So when we get into our simile software, we're going to start a new model, and since it looks something like a leaky bucket with energy in, energy out, I'm going to go ahead and enlarge this already so we can get a bigger picture. We will have one major reservoir, and we will call this Earth energy. And it's going to have flux in, which is going to be, we'll call it solar influx. And we will also have energy out, which we will call our IR. It's infrared radiation outflux. Okay. And with that in place, we can start to think about what we want to build in this model. Now, we can actually define the reservoir right off the bat. It's just zero. We're going to have no energy in here at all to start with. And so I click off of that and find that already 2 out of 3 of my parameters are solved. Wow, this is a really easy model so far, but the devil's in the fluxes. And so we're going to turn our attention to solar energy flowing into our reservoir with a quick overview of the units involved. Now start with simple F equals ma, force equals mass times acceleration, which has units of kilograms times meters over seconds squared. And this is also called a Newton. Now as I push my trebuchet towards the enemy forces, I am accelerating its mass and thus applying a force. But I can apply the same force to push the trebuchet a short distance or a long distance. Same force, but a different amount of energy was used. So to talk about energy, we need to know the distance the force is applied, and a joule is defined as force times distance. So we put another meters into the numerator to get kilograms meters squared over seconds squared, or we can just call that a joule. So the sun is putting out these joules of energy towards our Earth system, and it does it at a certain rate. Okay, now we got to get the rate idea in here. Rate means energy per unit time, or we can say joules per second, which is also known as watts. So since we can expand these out to the base units, we can say a watt is a kilogram times meter squared over seconds to the third power. Finally, we see how many of these watts are put out for each unit area of the sun. So we divide by square meters to get watts per square meter. Or in the expanded form, we find that that square meter area cancels out and we're left with kilograms over seconds cubed, but it's a bit easier for us in our model today to stay with watts per square meter. Now, our sun emits 3.865 times 10 to the 26 watts per square meter, a truly astronomical number. But that light has to travel to the surface of an ever-expanding light sphere. By the time this intense radiation hits our planet, it has traveled 93 million miles, or 1.5 times 10 to the 11th meters. Now, the energy density that left the sun has diffused out so much by that time. By the time it hits Mercury, it's dropped off from 3.865 times 10 to the 26 watts per square meters to a mere 9,116 watts per square meters at Mercury. By Venus, it's down to 2,611 watts per square meters, but we're trying to model an Earth-like planet, and here on Earth, the radiation reaches us with a mean value of 1,361 watts per square meter is the best modern estimate from a paper in 2011. So we'll use 1,361 watts per square meter as a solar constant in our model. That's the energy density hitting a flat surface perpendicular to the raised sun. So we need to play with that number a little bit here. So solar influx is going to have this solar constant coming in. Now over on the side here, I've written down all the pertinent information we're going to need. The solar constant, I've abbreviated SC, is 1,361 watts per square meter. I've given you all your units in red, except for one. And the reason for that is it's different flavor than all my other units, which use meters for its distance, are the radius of the Earth-like planet, 6,371 kilometers, is going to have to be converted over into meters before we can use it. So we also have the cross-sectional area of the Earth. Now this is the idea that if we had a flat surface pointed perpendicular to the rays of the sun, it would catch this cross-sectional area of the Earth, pi r squared. And that's the amount of energy that we're going to grab out of space of this watts per square meter that's coming in. Now that's going to be spread eventually over a whole surface area of the Earth, so we need a surface area which is 4 times the cross-sectional area. Temperature we're going to need is the energy in our reservoir divided by heat capacity. Heat capacity is going to be quite a bit more complicated. We're going to need surface area, ocean depth, density of water, and the specific heat of water for that heat capacity. The ocean depth we're going to set to 1 meter. This is what we call a swamp model. We're going to take the entire oceans of the world and spread them out all over the surface of the world just 1 meter deep. And this is going to simplify the uniformity of the radiation coming off, and we're not going to be circulating our atmosphere anyways, but it simplifies that aspect as well. So the density of water is 1,000 kilograms per cubic meter. The specific heat of water is 4,218 joules per kilogram Kelvin. And the Stefan-Boltzmann constant is going to come into our equations as well. It's 5.67 times 10 to the negative 8th watts per square meter Kelvin to the 4th power. And the IR out, this IR outflux over here, is going to be a basic black body radiator. And a black body radiator is going to have its surface area radiate at its temperature to the 4th power times the Stefan-Boltzmann constant. So with those equations in place, we can start to think about our model. I need a solar constant, and I'll abbreviate as I have over on the side there. So the solar constant, we have said, is going to be 1,361 watts per square meter. So 1,361, but I am going to play around with this, and I'm going to make it a variable parameter. And the minimum that I'll take it down to, well, for right now, is 1,321 watts per square meter. And the maximum is 1,413, because actually we don't have a perfectly circular orbit, and when we are at our closest approach to the Sun, perihelion, we are actually at closest approach 1,413 watts per square meter, and we're at our farthest approach from the Sun, which is in about June. This one's over in January, about January 3rd. June 3rd, we get 1,321 watts per square meter. So this 1,361 is the average through the year, and that's what I'm going to use for my beginning values. All right, so solar constant we know is going to influence the solar influx. Other things that are going to influence it are, well, not all the light that comes from the sun is going to absorb into the Earth. A lot of it reflects right back out into space. So there's a value that we refer to as the albedo of a planet. So albedo is defined as the amount of non-luminous light reflected off of a surface. So how much of the light that hits the surface of the object reflects back out using a 0 to 1 proportion, 0% to 100%. And for the Earth, light that hits the planet Earth reflects 30% of what hits it. So we're going to take the albedo and make that 0.3. Again, I might want to make this a variable parameter, so I'll do it a variable parameter all the way from its range, 0, absolute absorption of the radiation, to 1, absolute reflection of the radiation. So a black body versus a white body, basically, on there. Alright, so our value of 0.3 starts us off, and again, this is going to be part of the equation of solar influx. One last thing we're going to need is actually the cross-sectional area. What area is capturing this solar energy that's coming in? So I'll go ahead and do something that we call X-section, cross-section. And we see that cross-section is equal to pi r squared. And I won't put r as a separate variable. I'll just plug this directly in. Again, we might look for ways to simplify our model and not expand it out too much. But with pi r squared, all we have to do is say 3.14 times the radius squared, and the radius is 6,371 kilometers. Kilometers, that's not going to work, so 6,371. We just add 3 zeros. That's how easy this is to go from kilometers to meters. Alright, now that you've got that, then you can take that to the second power, and that is the cross-sectional area of your planet Earth. And that is also an influencer to the system. And I'll just clean this up a little bit so I don't have things going one over the other. And in the end, the solar influx is as simple as saying, well, it's the amount of solar radiation that comes in, the solar constant, watts per square meter, but not all of it absorbs in, right? So what you're going to multiply by here is actually not what gets reflected, 0.3, but its inverse. So we need to, in parentheses, say 1 minus the albedo, which is 0.7. I could have typed that directly in, but I want to make that a variable and play with it, so let's put it in as it really is represented in nature. And the last part is what cross-sectional area is capturing that energy, so times the cross-sectional area. And when you take all the units there that have just been plugged in, what comes in is watts, but watts are joules per second, as we talked about before, and the seconds are taken care of in the model. Each second, a certain amount of joules will be dumped into the Earth energy. So what is being dumped into the reservoir here is joules. Joules of energy. We start with 0 joules of energy, and it'll start to build up joules of energy, which will build up a temperature. So what about temperature? We're going to definitely need a variable for temperature. So we'll just call that T. And we see that temperature is equal to the Earth energy divided by something called the heat capacity. So I'll just put in a heat capacity here and say that T is going to be a function of Earth energy and heat capacity. All right, but we have to define those, so let's go ahead and get temperature defined. While we're here, we said it's as simple as the Earth energy divided by the heat capacity. Okay. Now, heat capacity is a little more complicated. It's surface area, ocean depth, density of water, specific heat of water. So let's just see, we've got the cross-sectional area here, but it influences the surface area. It's 4 times the cross-sectional area. So surface area I'll put over by cross-sectional area and compute it real quickly. Say that surface area is equal to the cross-sectional area times 4. Okay. Okay. I need to take away 1 multiplier. Yes, always make sure you got everything followed right. So we got the surface area. We are going to also need on this one an ocean depth. We are going to need a density of water, and we're going to need the specific heat of water. Alright, and these are all spelled out in our formulas over here on the side. We're going to say that the ocean depth is 1 meter. The density of water is 1,000 kilograms per cubic meter. The specific heat of water is 4,218 joules per kilogram Kelvin. And all those play into heat capacity. So feed them in as neatly as possible so that they don't go over the words. All right, that looks pretty good. And define heat capacity by our formula, which is heat capacity is equal to, oops, I forgot to put my surface area in. And that one's going to be a tight squeeze. Oh, that doesn't look quite as pretty, but it works out. I'll actually just move this down over here a little bit. Okay. Now, heat capacity can be defined as the surface area, and only once, times the ocean depth, times the density of water, times the specific heat of water. It's as simple as that. Okay. There's our heat capacity, and now we have a temperature generator. And the IR out on this side is, well, surface area times Stefan-Boltzmann times temperature to the fourth. Surface area being way over here is going to be hard to cross over neatly, so remember our ghost function. Just take the surface area, stick it up here, and reposition everything as we need, and give it an influence directly into our IR out. Surface area times Stefan-Boltzmann. We don't have one of those yet, so the Stefan-Boltzmann constant, I could plug that directly into our IR out formula here of the flux, but I know I'm going to need it again for another reservoir when we put the atmosphere in, so I'm going to keep this separate as a convenience. And I also want to show you how to put in these exponential numbers here. So with our Stefan-Boltzmann constant, we're going to define that as being 5.67 times 10 to the negative 8th, which we write out as capital E, negative 8 watts per square meter, Kelvin to the fourth power. Okay. And that is the Stefan-Boltzmann, which is going to influence the IR out. The other things that influence IR, well, temperature to the fourth power, so we need to have an influencer from temperature to IR out, and now everything's in place to define that black body radiation off the Earth. So given its temperature, it's going to radiate a certain amount of energy, which is its surface area radiating out at the Stefan-Boltzmann constant times the temperature to the fourth power. And if you check all the units here, what you're ending up with is temperature is in Kelvin. We have joules over here. What comes out are joules per second, or watts, out this side. And so all the nice little manipulation of our units works out perfectly. Right? Everything is nice if you want to check it. Alright, so that looks like a complete model that we can now say, without an atmosphere, what would be the temperature of a planet like Earth? Like Earth, right? So we get our run dialog box up and running. There it is. And we're going to put in a plotter as before. And the plotter is going to plot temperature. So I put in T for temperature. Now the run length, this is seconds, and an Earth is going to take a long time to equilibrate, a few years actually. So honestly, if I were to think about how many seconds I want to put in here, I'll do it at a month. Well, no, I'm going to actually put the event down here at about a month length. Every month I'll put out a report, so I'll put 300,000 seconds. That's approximating a month. And over here, I'm just going to plug this up to like 90 billion. I just need a lot of time to do this. My run settings, yeah, Euler, everything here looks fine. I'm fine with that. I don't want to report this every second. There's a dialog box off to the side here. I'm unable to quite show you. Let's see if we can get it. There it is. I don't want this to show every time step. I'm going to have it show every 10 time steps. It's really going to be slow if I do it every 10th of a second. So that looks good enough. And with all that in place, I think we can run this and figure out what the temperature of the planet's going to be. Up the temperature goes in Kelvin and finally plateaus up here, and what we're finding is it's coming in at about 254.5, 254.5. 5, 8. If we round up, that's 255 Kelvin. And in Celsius, that's -18, or in Fahrenheit, -0.4. In other words, we have a frozen planet in this case. But we could start to play with some of those slide bars that we made. We'd said that the solar constant is not as constant as it would seem because it varies throughout the year. So we will add solar constant here and say, what if we were to, let's just go down to its lowest possible, yearly extent and see what that does to this system. So if I stop, we'll start a new run, and we see that it comes in, barely below, right? 252.6 versus 254.6. Okay, so a couple of degrees cooler. And remember that Kelvin has the same scale, absolute scale as Celsius, but it is an absolute scale, so we never say degrees Kelvin. We talk about degrees Celsius, but a degree in Celsius is a unit in Kelvin as well. So a couple of units lower in Kelvin, I can just say it's a couple of degrees lower, because we can switch back and forth between Celsius here. Now let's go to the most solar energy coming in when we are closest to the sun. What if we were to stick that close to the sun? How much warmer can we get? So stop our run so that we can start a third one. And it pumps up here a little bit higher, and not a lot. We're up to 257. We're still frozen. This is a frozen planet all the way through. However, there's a couple of things I want to think about with this model. The albedo, the reflectivity of the planet, it's 30% of the light that hits our planet reflects back to space. But that's 25% of that. The light that hits the planet reflects back to space because of the atmosphere. And 5% reflects back because of the surface of the Earth. That adds up to your 30%. The atmosphere is 25%, so subtract the atmosphere from our model, and you're subtracting 25% of the reflectivity. So we could possibly play with another slide bar and add in the albedo and say, instead of it being 30%, what if it didn't reflect that much at all, and it was in fact 5%? That would be what you get with your no atmosphere. All right. Well, with that kind of a albedo, maybe we can get our temperature up a little bit higher. So we did boost up our solar constant as much as possible. We took down our albedo to where we think it might be without an atmosphere, and we'll say, is this good enough to keep a warmed planet, a liquid water planet? All right, well, let's stop and run and see how this works. It does come up to a higher temperature, and that higher temperature is 277.71. Right there, you're about 3 degrees Celsius, about 37 degrees Fahrenheit. You're still a cold planet. Our average surface temperature is 15 degrees Celsius, so this is a planet that is 13 to 12 degrees colder than our planet. So the atmosphere really does help, and so we kind of have just made a model that is what Jean-Baptiste Fourier made in the 1700s when he said that clearly the temperature of this planet is augmented. It's increased by the interposition of this atmosphere, where visible light can come in through this atmosphere easily, but this non-luminous heat, or infrared, trying to get out is trapped. This model has no trapping. This is a cold planet, so we are very grateful for our greenhouse effect. It brings us up to a habitable level. Now, we could play with some other things along these lines and say, in the distant past, we actually had a fainter sun. All right, and we could even put a controller over here on the solar constant. The solar physicists tell us that our sun was probably 30% less luminous back 4 billion years ago. So you can have this ramping solar function over here that ramps up over geologic time and see what that does to your model with no atmosphere. But that's as far as we want to go this time. We've built a nice no atmosphere model, and so that ends part 2. And in part 3, we're going to come back and actually make an atmosphere. So see you then, and thanks for your time.